Hello, welcome to SPMM Revision on Demand. In this podcast, I will discuss three nomograms that are important for critical appraisal of medical research. First of all, what is a nomogram? Mathematical equations are made of several variables. If you know the values of all except one variable, then the unknown can be deducted from the mathematical operations defined by the equation. A nomogram is a chart that helps us to do this without the need for a calculator or computing skills. Instead, all you need is a ruler and a pencil to connect dots. There are three nomograms used commonly when practicing evidence-based medicine. I have made a table explaining their usage. Bayesian nomogram is also known as Fagan's nomogram. This is used to calculate post-test probability from pre-test probability. NNT nomograms help you to calculate the new NNT value for your clinical sample from the relative risk reduction observed in a randomized controlled trial. Altman's nomogram is also known as sample size nomogram. This is used for the purpose of power calculation. As you know, power calculation is indeed a misnomer. We do not calculate power, but we calculate the sample size required to achieve a specific power for clinical trials. Firstly, let's see the Bayesian nomogram in detail. This nomogram is used in the evaluation of diagnostic tests. When you conduct any diagnostic test, the most important question for a patient with a positive result is, what is my chance of having the disease for which I was tested? The post-test probability is the probability that a patient scoring positive on the test actually has the disorder. Once we know the pre-test probability and the likelihood ratio of the test result, we should be able to find the post-test probability from the chart shown here. Pre-test probability is nothing but the prevalence of the condition in your clinical setting. A straight line drawn through the pre-test probability and the likelihood ratio should give you the post-test probability. Let's assume that the prevalence of schizophrenia in your early intervention team setting is 70%. A new MRI test for schizophrenia has a likelihood ratio of a positive test of 10. What is the probability that one of your patients who tests positive for this MRI test actually has schizophrenia? To answer this question, draw a straight line joining 70 and 10. Extend this further till it touches the third vertical line. The answer is 95%. Next, let's consider the NNT nomogram. NNT stands for number needed to treat. This nomogram is used in the evaluation of beneficial or harmful effects of a treatment on the basis of an RCT. When you offer any treatment to a patient in your clinic, the most important question for the patient is, what is my chance of responding to this treatment? NNT provides a useful summary measure that captures the utility of a treatment. NNT refers to the number of patients that need to be treated using an intervention in order to obtain one additional response when compared to either a placebo or a standard treatment. NNT is nothing but the inverse of absolute risk reduction, ARR. ARR itself can be expressed as a product of CER and RRR. CER refers to the baseline response rate without the treatment. This is also called patient expected event rate, or PEER, when applied to a clinical sample. RRR refers to relative risk reduction. A straight line drawn through the PEER and RRR will give us the NNT. Let's say 50% of your patients with depression get better without any intervention. That is, PEER is equal to 50%. A meta-analysis of RCTs provides a RRR value of 50% for the efficacy of antidepressants. How many of your patients need to be treated to get one additional response compared to the baseline? To answer this question, draw a straight line joining 50 and 50 in the first two columns, and extend this further till it touches the third vertical column. The answer is 4. Finally, let's consider the Altman's nomogram. This nomogram is used in the calculation of the required sample size for a trial. Sample size depends on the standardized size of the expected effect, type 1 and type 2 error rates, that is, p-value and power. If these three values are known or assumed, the sample size can then be estimated quite easily. A straight line connecting standardized mean difference and power will touch the sample size scale, that is the diagonal, at two platforms. Each platform corresponds to a specific p-value, either 0.01 or 0.05. Trace the appropriate line to read the scale. Let's assume you want to recruit for a study that aims to find a standardized difference of magnitude 0.75 with 85% power. Draw a straight line joining 75 in the first column with 85 in the last column. This will touch p is equal to 0.05 platform at the value of 60. So at p is equal to 0.05, the sample size needed is 60. Now it's time to ask yourself a few questions. Thank you for choosing SPMM course for your revision.